In this example, we're going to use the direct comparison test to show that a series diverges. So we're being asked to determine whether or not the series n equals 1 to infinity of e to the 1 over n converges or diverges. So again, the challenge, at least in my mind, the challenge in applying either the limit comparison test or the direct comparison test is to figure out what am I going to compare the series to. Looking at these terms, this is 1 over n is always positive, which means that e to that power will always be greater than 1, which means that these terms are always going to be greater than 1 over n. So that's the series I'm going to choose to compare to. Okay? So we're going to apply the direct comparison test with the series from n equals 1 to infinity of 1 over n. So certainly, our series here all have positive terms. And like I mentioned, e to the 1 over n is always greater than 1. As long as, well, in particular, n is positive, but for this example, n greater than or equal to 1. Which means if we divide both sides of this inequality by n, the inequality does not flip, so we get e to the 1 over n, all over n, is greater than 1 over n. The series from n equals 1 to infinity is of 1 over n diverges. That's the harmonic series. The harmonic series, if you will, is kind of the most famous divergent series because the terms here go to 0, but the series does not converge, right? You're adding things that are getting smaller and smaller, but they're just big enough to make the whole series go off to infinity. Okay? So in some respects, it's the most famous divergent series, if you quantify famous, if you will. All right? So since this one diverges and it's the smaller series, the original series must also diverge by the direct comparison test.